Okay, well, it's 7:30, so I'm going to go ahead and start the session. So welcome everyone to Theme 15A, Ring of Fire, Geochemistry and Geohazards. So please bear with us in this, one of the first few virtual sessions of Goldschmidt 2020 in this brave new world of remote conferencing. And I'm sure you'll all join me in thanking Jackie and everyone at White Iron Conferences, as well as the Scientific Organising Committee, for pulling all of this out of the bag on such short notice. So I'd like to start this session by providing a brief introduction to our speakers, who you can see here on screen. We have Siggy Gislason, Research Professor at the University of Iceland's Institute of Earth Sciences, expert in volcanic geochemistry, including the environmental impact of volcanic eruptions. We have Don Swanson, US geologist and field volcanologist with extensive and wide-ranging experience and expertise in Hawaiian and arc volcanism. We have Bridget Smith-Conter, a geophysicist at the Department of Earth Sciences at the University of Hawaii at Manoa, who uses geodesy to understand tectonics and volcanism on Earth and other planets. And we have Diego Melgar, a seismologist and geodesist in the Department of Earth Sciences at the University of Oregon, who works on understanding large earthquakes and developing early warning systems. So I hope you've all had the opportunity to listen to the introduction to this session and to the talks provided by our keynote speakers. And I would like to thank all of our speakers for their wonderful talks and insightful perspectives on geohazards. So theme 15 is about the future of our planet and how we live on it, our science and our interaction with society. And this is session 15A, convened by Ken Rubin of the University of Hawaii, who's here, and me, and I'm Marie Edmonds from the University of Cambridge. And here we'll focus on the major scientific and social challenges associated with geohazards, including volcanic eruptions, tsunamis, and earthquakes, and the growing challenges associated with the linkages between geohazards and population increase, urbanization, and with human and environmental health. Critical questions for the future involve understanding the hazard, monitoring the physical and geochemical processes, providing early warnings, and the communication of hazard and risk. And intimately linked with these challenges are education, training, and research. And in this session, we'll discuss with our panel some of these issues, and we also welcome questions from the audience. So you can ask questions by typing them into the chat box on your screen, or putting your hand up, and we can unmute you and you can ask your question verbally if you want to, or you can type it into the chat box. So that's how we're going to do this. And before we start, I'm just going to give a kind of brief synthesis of the talks. I hope you've all had a chance to listen to them. They really are fantastic talks. And they've raised a number of interesting areas for discussion. So Siggy provided a very engaging talk about the hazards associated with Icelandic eruptions, ranging from ash hazards for aviation to yocalypts to lava flows, using the Eyjafjallajökull eruption as a case study. And Don Swanson gave us a fascinating overview of the 2018 Kilauea Lower East Rift Zone eruption and the particular challenges and triumphs in scientific understanding that emerged out of that. Bridget explained how geophysical data can be used to understand the temporal and spatial emergence of geohazards during eruptions, and highlighted really spectacular examples from the 2018 Kilauea eruption. And finally, Diego showed us the really exciting potential of using high-resolution geodetic data to train algorithms to classify earthquake magnitude and predict shaking, a development which will undoubtedly revolutionize earthquake hazard mitigation. And some clear themes emerged from these talks that I hope we'll have time to really probe deeper into in this session. And these include the complex and multi-hazard nature of many of these events, including multiple physical events such as flooding and ash, earthquakes and tsunami, and lava flows and earthquakes. And there are clearly challenges associated with communication of hazard and risk, educating the public, developing interagency collaborations, balancing operations with research, developing innovative real-time monitoring and warning systems, all on top of the fundamental challenges of understanding the hazard itself. And it's quite clear also, what really emerged for me was that the boots on the ground data gathering, instrumentation and sample collection really underpin everything that we've talked about, from calibrating geodetic data for large earthquakes, using dense networks, to providing data for the VAC in London to forecast ash hazard. So I'm going to kick off the questions, and I would like to ask a question that really came to the forefront for me looking at all of these talks, which was, what are the challenges involved with communicating and coordinating between government agencies? Now, I think this has relevance to all of your talks. So perhaps I'd like to ask Don first for his reflections on that for the Kilauea 2018 eruption. Can you unmute yourself, okay?
Was that, Marie, was that question addressed to me or?
Yeah, yes, please,
Okay,
Don.
sorry. Yeah, I was, well, in 2018 at Kilauea, there were two distinctly separate areas that had, in which we had to deal with the public and governmental officials. One was in the lower East Rift Zone where the lava flows were erupted. And there were relatively minor issues regarding scientific access to the area. They had to go through, get approval from county civil defense and so forth. I didn't work in that area, and so I'm not directly familiar with them. I heard that there were small glitches, but they were pretty much evened out. So I think that the interaction between the scientists and the local authorities worked quite well. I was up at the summit of Kilauea, which was 40 kilometers away, and was collapsing during the event. This is in the national park, and there were a couple of things that I noticed that went wrong. Maybe three because I was there, but the two that I noticed were, one, that we didn't really have a plan internally in the USGS for scientific work of boots on the ground type. It was really fantastic monitoring that was being done of what was happening, but we didn't have a means to direct people to go and make specific measurements at specific locations of the developing fractures and so forth. The other issue is a systemic one, and that is that the national park controls the land that's within its borders. And this means that everything that is done by the scientists has to be approved beforehand by the park. Usually that works very well. But in this case, there were some things that we wanted to do immediately. You just get an idea and you want to do it right now. And we didn't have the time to, go through the hoops with the Park Service, but still that was mandatory. And so I would say that I'm not pointing any fingers. I'm simply pointing out a problem, and I think that that it would behoove us to make means available before the next event happens, so that scientific access could be understood as being approved. The scientists are the experts, and the land managers, I think, will or should realize that and allow us to conduct our research in a timely fashion. And I think there were issues when that was not timely in 2018. So I don't want to sound like, sour grapes, because I think overall things went remarkably well in 2018. But because they did, I think we can also point out certain areas where improvements can be made.
Yeah, thank you, Don, for those perspectives. Siggy, I wonder if you could come in and give us the Iceland perspective on these kinds of issues.
Yeah, well, Iceland is a small community, just 360,000 people. And many of the people are various institutions that has to focus on this are our former students. So we're like a big family within Iceland. So for example, now we're preparing for a possible eruption within the Grímsvötn, this summer, and we've already had a couple of meetings, and there's also preparation. I just had with meeting with my students to prepare for ash sampling to assess the pollution. So we need to issue a statement as early as possible to the farmers whether they have to worry about fluorosis and bring in the grazing stock. So I think communication within Iceland is very good between the Icelandic Met Office, University of Iceland, and the survey. And what we saw during Eyjafjallajökull, that the extremely important communication between the Icelandic Met Office and the London VAC, the Volcano Advisory Committee, and I guess that Mary is under the UK Met Office. So following the eruption, there was signed a memorandum of understanding between the Icelandic Met Office and the London VAC, and I think even the British survey, about exchange of people, to actually develop a personal contact between the people working at these, because in the very beginning of the eruption, there's just an intense communication. There has to be personal knowledge and communication because you have to act so fast. And the eruption in Eyjafjallajökull, that was my case study, started early morning 2014, and by midnight, the airspace in Western Europe was closed. And I mean, they have to issue a warning they're expecting eruption, and then the London VAC starts to run their models, climate models, etc. And then as soon as they get more information on plume heights and possible grain sizes, they can start to run real models. So this was, and also there was some hesitant and some strain between UK and Iceland right about the time in April 2010, because UK had put Iceland on the list of terrorist nations to stop the flow of money out of London following the crisis. So there was a very strange atmosphere. So I remember there was a delegation coming from UK to kind of smoothen the process, and I tried to start with a joke, that's good that we have plenty of ash but no cash, and no one laughed. Okay, so I think our strength is a small community. The Met Office runs a fantastic website that is most often completely open, and we have 200,000 experts on geology and volcanology in Iceland, when we are there, and there's actually a lot of, well, that can be sometimes too much to handle. Okay.
Yeah, thank you, Siggy. I think you're right. You brought out a really interesting point, which is developing these individual contacts, which can work really well in these crises. Diego, I don't know if you want to come in here as well, because I think this question is relevant to what you're trying to do with the early warning, because presumably, in order to make this work, you need to have a network of interconnected agencies to deal with the alerting and various other aspects of the system.
Yeah, that's right, Mary. And I think one thing that is fundamentally different between the earthquake early warning problem and what's been discussed so far by Siggy and Dawn is that all the work needs to have happened before the earthquake, because once the earthquake occurs, earthquake early warning needs to be completely automated. There can be no human interaction. So unless you have done your homework and done it really well, there's no time for second guessing or for adapting. Once the earthquake strikes, that's it, you're done. You either did it well or you didn't do it well. But really, besides the science challenge of earthquake early warning, which is what I talked about, perhaps the most pressing open problem is the communication of what can earthquake early warning do for you. And that's where the interaction with government agencies becomes really important, because the USGS or the university scientists, we are not in any capacity trained to go talk to the local tribes in the state of Oregon, for example, about how earthquake early warning is going to work for them and to help them to design a plan of how to respond with earthquake early warning. Sure, I can explain the science and I can tell you why it could be 10, 30, or 60 seconds. But ultimately, it's up to the regional emergency managers, local leaders to decide for themselves how to use this. And this is a gigantic undertaking, especially in the US, because earthquake early warning spans, 1,000 miles, more than that, actually. And if, think of the diversity of people that are involved in responding to earthquake early warning, it really boggles the mind. And everybody responds differently, from individual communities to a utility, Pacific Gas and Electric, to private companies. So that's where actually building a network of interconnected entities who all decide that they want to benefit from earthquake early warning and come together has become probably the biggest part of the earthquake early warning effort. Now that it's matured and the technology is there, it's almost like the seismologist doesn't matter anymore. Now what matters is how to talk to people and how people connect with each other and with their public agencies. And it's been really beautiful to watch. It's a little like ordered chaos right now as we're learning about earthquake early warning in the public setting. But it's been very interesting and really, truly beautiful to watch people take that and decide that they're going to work together and make it happen.
Thanks, Diego. So there's a question for Medina Payton here, and she would like to ask if the panelists can share any experience they've had with issues of miscommunication in the social media or wrong information that perhaps have had consequences. Diego?
This isn't so much miscommunication as, well, it is miscommunication. So we had an earthquake, a series of earthquakes in 2019 in California, the Ridgecrest earthquakes. They happened just a few months after earthquake early warning had been turned on, so to speak. And the way that earthquake early warning was set up, it's based on the intensity of shaking. So if we forecast that the intensity of shaking is not going to exceed a certain threshold, we don't issue an alert. And the seismologists, pointy-headed scientists, had decided on a certain level of threshold that was not expected to damage buildings, but expected to be felt. Anything lower than that threshold, we wouldn't issue alerts, even if we detected it. Well, it turned out that the earthquakes happened and millions of people felt the earthquake, but it was so imperceptible in the LA basin that it didn't meet our threshold, so we didn't issue an alert. And because we hadn't done our job properly of socializing what this meant, this threshold level, the firestorm on social media of people saying this earthquake early warning system doesn't work because I didn't get an alert was gigantic. When we had to basically go over the next 2 weeks into putting out fire mode and explaining that the system worked exactly as we had designed it, it's just that probably it shouldn't have been the seismologist making the decisions about the thresholds. We didn't really consult people that much. So that was a huge lesson, that we were very good at the science, but we weren't very good at the people part of earthquake early warning.
Yeah, thanks, Diego. Bridget?
Yeah, I would just like to add to that social media has really revolutionized how we communicate with ourselves and with the public. But as a scientist, we learned a lot from the Ridgecrest earthquake, in that you couldn't get the science information you needed from your colleagues immediately via email or even on a forum website without the added essence of social media. People were twittering results in real time. Scientists were. And those that weren't on Twitter were missing out tremendously. We were wondering where all the information is coming from. So I am not by any means a trained Twitterer, but it's a really good aspect of engaging with your own community and learning how to deal with all these early response activities. Also, I was in the Ridgecrest earthquake that Diego is talking about, and I was visiting LA at the time when this happened, and it took over a half hour to find out the magnitude of the earthquake. The web was just flooded, and the USGS's website went down because so many people were online. And so had I actually had an ability to reach out to colleagues in a different manner and to the public, I would have been informed a lot earlier. Luckily, there wasn't any particularly problems in LA as a ramification of this, but we all need to sort of step it up in terms of how we communicate with each other.
Yeah, so there are clearly pros and cons with the tweets in real time, in rapid response. I wonder if there are any volcanic examples from either the Icelandic eruptions or the Kilauea 2018, where information was tweeted out on social media.
No, well, I don't know really if we have examples of that, but the radio is very powerful. At least, I mean, now I'm talking about 2010 and before that. You know, and for example, I know that the earthquake that we had here in 2000, you know, the size of, because the Met Office was tuning all their seismometers to get the precursors of the big one. And then we got the big one. And it took a long time for the Met Office actually to get the number. But then some guy just went on the USGS, you know, website and got the, you know, magnitude of it right away and just called it in. And that was the first, the way it came into the media. And also in Eyjafjallajökull, we had a lot of, you know, when we were expecting the eruption and the summit, we had chemical sensors in the rivers and flood heights and temperature. And then there was this talk show in the morning when it was just about happening. And then the guy in the talk show said, oh, you can go to the Icelandic website and you can just have a look at it. You can see how the chemistry is going to change in time when the flood comes down. And everyone went on it and the whole thing went down. So we had no idea what was happening, you know. So things like this, we have to be careful about that. Another thing I can say that during the Eyjafjallajökull eruption, that there was our president at the time, he was a very outspoken person, brilliant person. But, you know, they were talking about possibility of interaction between the Eyjafjallajökull and the big Katla volcano that is bigger and produced something. And, you know, I think he was being interviewed by BBC or something and said, well, of course, the other one just east of that is much bigger and you ain't seen nothing yet. And then after that, whenever we had to communicate with the public, we had a list of words that we were not supposed to use, you know, and so forth. But I have to say, I'm not on Facebook, you know, one of the oldies, so I can't give you an example of how the social media has affected us. Okay.
Yeah, that's great.
Yeah, Kilauea in 2018, we had kind of two levels of social media interaction. One was an internal sort of USGS and cooperator level with something called Mattermost, and that worked exceptionally well to keep everybody, you know, all the scientists informed in real time. Sometimes there were entries almost before the earthquake stopped. They were just really rapid. But more importantly, the social media that involved the public, which I had nothing to do with, but I've talked a lot with our public information specialists, presented a lot of problems. There was a lot of misinformation that went out, but a lot of good information as well. And the people that I talked with in the USGS that dealt with this said that on balance, social media was a positive in 2018, but they had to put out a lot of brush fires that were started by inaccurate reports on social media too.
Yeah, it's sorting out the good from the bad, isn't it? It's on that topic actually about educating the public. And Don, you mentioned in your talk about efforts that the USGS have made to sustain the education of people that live around volcanoes in Hawaii for a very long time. So that even between eruptions, you know, they're being educated about the volcano. You mentioned that at least a fraction of the population were. I mean, how important is that, do you think, is to sustain a very deep policy of trying to educate the people that live around the volcanoes?
It's certainly not the ultimate answer, but it was a big help, I think. We had a sort of a loyal cadre of residents in the volcano area that we've given many talks to, when we have a weekly essay in the local newspapers about volcanoes. And the people that pay attention to that were really several steps ahead of the general populace who didn't understand it. And of course, they are able to act as our emissaries. They can tell their friends what's going on, probably in words that are more readily understandable than to have the scientists do it. So I think, well, just as in Iceland, probably the closeness that we have on the island of Hawaii to the residents really helped a lot during the crisis in 2018.
I think if I can add to that, I think continuous flow of information, you know, to the media, and we have fantastic people at the civil protection that are really, really good at communicating, and they are the best friends of the media. I mean, they've also been doing now the COVID, and they're just fantastic, and there is a complete trust in them. And we found out just to have a complete, well, not complete, but really, really good flow of information to the general public, and engage them in when we discussing decisions. And so, and the Icelandic Met Office, I mean, the weather is ever changing in Iceland, and we, you know, you really have to plan your things around it. Most Icelanders, they visit the Icelandic Met Office website every day. So, you know, it's there. So that's for a small country like that is making things much easier.
So what about from the earthquake perspective, Bridget or Diego? What are we doing, and can we do more? Is this an issue, education of the public?
Diego, you want to take this?
Sure.
Okay.
I mean, the answer to can we do more is always yes.
Yeah.
I think seismologists are very active on Twitter, remarkably so, especially after large earthquakes. I see so many pictures of, you know, fault scarps and surface evidence of faulting, and people respond really well to that. I oftentimes think, you know, I'm not active enough on social media, and then I realize that as a scientist, you kind of make a calculation, you know, because it takes time. So do you want to spend your time figuring out where the data is, downloading it and working on it, or do you want to spend those minutes interacting with the public? And both of those pursuits are equally valuable, and not everybody values their time the same. It's not to say that one answer is better than the other. And I am really appreciative of my colleagues who spend a lot of time on social media, because they do a public service that is sorely needed, especially nowadays, you know, when science is so frequently devalued. Having actually voices of authority that speak in a candid way to people and reach them is incredibly valuable. I think that we could do more, yes, to educate the public, but I think with that in mind, we could do more to teach scientists to interact with the public in this new way. Again, not everybody needs to spend as much time on it, but some will choose to. And then one thing that I think we could do is to restructure academia and science to value that. So if somebody spends a lot of time on Twitter, that's not going to help them to get tenure. And they really should. If they actually reach people and have an impact beyond, you know, their H indices and their citations, why are we not valuing that the same way? So I really do think that we could do that. So yeah, I mean, the answer is always we could do more, for sure.
Yeah, thanks, Diego. Bridget.
Yeah, if I can just add to that, I completely agree with everything Diego just said. Also, there is a big movement to better educate the public. There's an initiative called the Great Shakeout that is run through the USGS and other mediums. And this is a once a year, excuse me, right around October 15th. It's the third Thursday of October, and it's a participate in earthquake preparedness and preparation moment. Sometimes it's done live around the world. Other times schools or institutions are able to just carve out an amount of time to prepare on their own. But it's like an earthquake drill. And the mantra behind this is the great drop, cover, and hold on. And it's what to do in the case of an earthquake. Of course, that's the immediate response, and we all should try and participate in that and support others that are trying to educate people through that forum. However, there's also the aftermath of, you know, that's the moment you're in and what you do in an earthquake versus what you can do ahead of time, and then also how you can interact with scientists, the public can interact with scientists after an event, and what they can learn from the information that's out there.
Those are really interesting perspectives. Thanks for those answers. We've got another question from Adina, which is for Diego. So it's, what is the prospect for getting warning systems that can be early enough to make a difference in cases like the Japan earthquake and tsunami, the Tohoku earthquake?
Well, good, I think. Early warning systems are getting better and better. I think there's still a challenge for the really big events. The challenge for the really big events is that, you know, earthquake early warning is not necessarily precision science, even if we'd like to think so. Responding in real time with seconds to spare is really hard. Identifying things exactly as they're unfolding right now, this second, is really challenging. And we're getting better at it, but the truth of it is that there's still, you know, scatter around our predictions. And the challenge with the really big events is that, you know, for smaller, more frequent events, if you're slightly kind of wrong, it's fine. Everything's fine. But with the really big events that are almost once in a generation type events, you really have to get it right, because those are the ones that are really, really important. And right now, I don't think we're there with earthquake early warning. We will get there, and there's a clear path to getting there. But, you know, I live in fear of an actual magnitude 9 happening here in the Cascadia subduction zone right now today, because we are not going to get it right. We're working to get it right, but we're not there yet. And imagine the black eye if the magnitude 9 happens and we just screw it up. This is going to last for my entire career. So that's the real challenge of those. And we have a clear path forward, and we will get there, but these things take time, they take funding, and they take effort. So this is, again, where we need to better interact with the public to communicate these things that we know are deficiencies or incompletenesses of our efforts. And I don't think we're doing that nearly as well as we should.
So Diego, do you think the effort needs to be focused on understanding the hazard, the physical mechanisms, the physics of tsunamis, or is the effort involved in the modeling side?
Yeah, I mean, that's an almost philosophical question. I oftentimes like to talk about the top-down versus bottom-up approach. Do we have the science motivate the hazard systems, or do we have the hazard systems motivate the science? And each society picks differently. Japan picks to have the hazards drive the science because they're facing hazards every day. Whereas here in the US, we tend to think that first we do the hard science, and then if we find something useful, we'll build an earthquake early warning system. That's a personal choice for every society, but undoubtedly you can't build a better earthquake early warning system unless you learn new things about earthquakes that you can leverage. You can't advance applications without advancing knowledge at the same time.
Yeah, thank you. And of course, time is critical for these early warning systems for tsunamis, and in some ways for the volcano applications as well. And I was wondering, actually, Bridget, from your presentation, how much of that amazing INSAR data was available in real time? To what extent is now INSAR, you know, within the fabric of volcano monitoring at an observatory level?
Yeah, that's a great question. So in the case of the Kilauea event, it took roughly 12 hours of time before the data was acquired by the ESA satellites, the Sentinel satellites that we used, and then provided on a platform that was open to the scientific community to download. So that's already a 12-hour roughly offset in time. And then from a processing side, there are various ways one can go about pulling out the important information out of SAR data. And in our case, it would take roughly 6 hours to download and process the data and then provide it on a website where people could see it. So you're looking at almost a 24-hour turnaround time, which in terms of immediate response is not super helpful, but better than nothing. We also have to think about the longevity of SAR and what satellites will be available in the upcoming decade. Good news is that NASA is partnering up with the Indian Space Agency to offer us a new satellite that's called NISAR that should be launched in 2022 if all goes as planned. And that will be a great opportunity for us to continue to be able to observe natural disaster events like the one in Kilauea. The interesting thing about this is usually these satellites are tuned with a cadence or a repeat observation time of about every 6 days. However, in the case of a national disaster or a crisis or an emergency, government agencies and the scientific community can request that the satellite be specially tuned so that it can observe more frequently. And that was what happened at Kilauea. It took about 4 or 5 days after we thought the initial eruption was about to begin that the Sentinel satellite was actually able to be upgraded in terms of observational time. But it worked. It was great. For 4 months, we had data coming in every 3 days, and we could provide that within about 18 hours to the public.
Yeah, well, thanks, Bridget. I think the Kilauea eruption in 2018 and the recent Icelandic eruptions are really great examples, actually, of how there's such a diverse amount of geochemical and geophysical data together. It really provides an integrated picture. I can't think of any two better examples, actually. So there's another question come in, and it is good to hear how people living in areas that are primed for a hazard, volcano in Hawaii or Iceland, or earthquakes in LA, are receptive to information from the scientists. What have you learned from your experience about how to reach populations that are not primed? For example, when the volcano erupts in Iceland, but then people in Central Europe have to turn their lives around. So do you have any insights on how to reach them and avoid misinformation? Siggy, do you want to have a go at that one?
I think well, it was interesting during the Eyjafjallajökull eruption when I came in after the sampling. You know, the department here was actually crowded with journalists, and they all came in from US because you couldn't fly in from Europe. But these were fantastic journalists. They were not trying to sensationalize. You know, I specifically remember, you know, German Precision. There was a journalist from Speaker, you know, he had it all right and, you know, corrected me if I was saying something wrong. So, of course, that caught all the attention of people in Europe because, I mean, all their air fleet, well, 68% of their air fleet was grounded. So it was a spectacular phenomenon. It was the first news in Europe for many, many, many days. But to reach the attention of Europe, for example, with a effusive eruption like the old Laki, you know, in 1783 to 84, I think that's something that will grow on people. You know, we learned something from Holaröin. No one in Europe really knew that, you know, there was a large, actually the largest eruption in Iceland in 200 years, because the general public was not allowed in. It was like a mousetrap. We had to travel in the flood of possible Jökulhlaup. So it was more or less just scientists paying attention to that. But, you know, the plume got into Europe. You know, it is in some station, it was the largest plume that measured that year. But it didn't pose direct threat to the general public. It didn't affect the general public there. So I think, you know, it's you know, if it is something spectacular, you can then touch people like in Europe. But if it's just a ordinary eruption, not affecting their flights tomorrow or something like that, it's harder.
So staying on that theme of the effects of geohazards in different areas around the world, it seems clear to me that advances in monitoring and forecasting are being largely driven by first world countries, where mortality rates due to geohazards are already very low. I mean, it's in California. I mean, the mortality rate in large earthquakes is very low compared to Haiti, for example. How can we roll out these benefits for the good of all? So we should be doing more to do this, I think. What are your thoughts on that? And then Sigrid.
Earthquake early warning is super expensive. You know, we're talking about $50–100 million to build, just to build out the system. Never mind, you know, the $10, $20, $30 million to operate it every year. Obviously, Nepal doesn't have that amount of cash. A revolution has occurred in seismology and sensors. You can now get super cheap sensors for ridiculous amounts like $1. You can build an accelerometer, a MEMS accelerometer for $1. If you add the electronics, maybe you're at $10, $20, $30. I think the way forward is through these kinds of efforts. There's an initiative called Open EEW that is fairly new. And the goal of that initiative is to make publicly available these kinds of designs for sensors, but also software so that somebody could say, hey, I am the city of Kathmandu and I have $20,000, not millions, but $20,000. I could buy 50 of these cheap sensors and download this code that is being worked on and vetted by an open source community. Whether that will work out, I don't know, but it's a really interesting model that is completely different from the centralized sort of government funded approach that exists now today. I don't see any other way forward except these kinds of efforts that we need to think differently than the way we've been thinking about them.
Yeah, thank you. Siggy?
Yeah, well, I want to use the analog for the exploration of the use of geothermal energy. We run, well, I should say we, I haven't been involved with it. The United Nations, they run a geothermal university here for the third world, or whatever you want to call it. And there they've trained, tens or probably, hundreds of students. They come here for a year and a half training, really hands-on training. And they are the ambassadors, in Central America, Africa, and so forth. And now, something can be built on that. But of course, I think this is a small scale, but small scale and kind of maybe a little bit old-fashioned. But if we could do this, something like what we do today, online, World University, to educate and try to get personal contact. Personal contact is so important in heavily affected areas, and then take it on from there. There's just one thing I want to add a little bit on a different matter before I forget it. Is one of the hazards we have here in Iceland is actually geohazard tourism. And one of the largest, all the Icelanders, they're so excited about, they watch the web, but they're all specialists, and they want to go to see it. So that's one of the biggest operations is to, where to stop them, because people get so angry if they're stopped. And one of the largest rescue mission in Iceland happened in January 91 when Hekla erupted, actually 2 hours before the Bay War. I think it was 21st of January or something like that. It was, it was a beautiful weather when the eruption started. Then we got a blizzard, and there were 20,000 people stuck in the snow on the pass into Reykjavik. It was a huge rescue operation. So that's one of the side effects.
Yeah, thanks for those perspectives. This is clearly something to focus on for the future, I think, these kinds of issues. So I had another question that came in, and it's for you, Bridget, I think, a question about can you have access to more satellites to receive data on a daily basis, or is the ESA satellite the only one which produces INSAR data?
So it's a great question. No, there are plenty of other, at least a handful of other satellites currently observing the Earth, able to detect land deformation. There's a Japanese satellite that's currently up and running named ALOS, for example. That's just one of them. We don't know how long all of these satellites will be up and running. On a moment's notice, something could go wrong. However, most of these data are available to at least the scientific community through a consortium of scientists that have pulled together access to the data. The ESA data, however, is free and available to anyone, as will be the NISAR data in the upcoming years. But yeah, there is a concern about limited opportunity to be able to do something with this data. However, I would say that there are a couple of groups maybe in the entire world that know what to do with a large SAR data set properly to be able to extract information like INSAR. So there's already a filter with what one can do, but one can download a SAR image and look through a cookbook that's public online that allows one to be able to do some simple data processing. And that's an activity that we do in classrooms at the college level all the time. to train our students in how to use INSAR data. So there's a range of answers here, but the idea is to promote free access to this type of data as in the years to come.
Thank you, Bridget. So I also wanted to ask, Don, in your talk, you talked about the tension between doing research during a crisis and the operations. So on the one hand, there's a critical time component, you have to get the monitoring done, but on the other hand, you want to understand the processes going on. Could you say something a bit more about that, Dawn? I mean, specifically, how do you go about persuading the agencies that need to be persuaded that research is actually important and it's required to spend time on it in a crisis?
Well, I think it's not an easy matter to convince others that research is necessary during a time of crisis. But the question that you want to ask is, how can I do better the next time? And the way that you can do better the next time is to learn more about what's happening at the current time. And so that's where the research comes in. And I think that is a topic that has been discussed a lot in academic circles, is that how you can get NSF money quickly, but it's not been discussed enough, I think, in the agency that I work with, the USGS, that in which the gut reaction is the natural one, is that you want to go out and save people's lives and property if you can. But it really, research should be built into a response, I think. In 2018, it worked quite well in the lava eruption area, lower Puna. But it wasn't because it was planned, just because that there were a lot of things to do and people did it. At the summit, not so well, as I've mentioned. And I just think that contemporary research has to be remembered during a time of crisis. Can we learn something that can make our job better the next time we do it?
Thank you, Don. Siggy, do you have a perspective on that from Iceland?
Well, it's kind of hard to plan an eruption. I had a German project manager that said, you're going to bring the students out of their carbon capture and storage project and let them work on volcanoes. We have an EU grant to, and we have a, project to deliver. You can't do that. So, I mean, you had to kind of improvise. And of course, there are things that that has to be measured. But I remember sometimes you kind of just have to step back and when you're there and be like a child. Give you a few minutes to enjoy just the beauty of it. And then it's really hard to get out of that mode and be pragmatic. What's most important? Which data do we have to save? And then you just go on a sampling streak because, you might be the only one to go in there and get it at this time. And you just have to be as creative and just to sample and be prepared. I mean, you're never prepared for everything. And for example, I think we lost one of the best samples we could have taken in the early stages of Eyjafjallajökull. There was just a effusive eruption on the flank between the glaciers. And we were up there and watching the beauty of it. And there was this big, lava flow that went, hundreds of meters down into a canyon. And then there was actually I think a dam or something in the lava. And all of a sudden it burst and you got this incredible mass into the canyon. There was a lot of snow there. And there was a beautiful hydromagmatic eruptions in there. And we were just, wow. And we got so few samples, just pitiful samples of it, because there was something very special. We were all sampling the different ash. So it is, to some extent, it's always going to be an improvisation because you are going into uncharted terrain and making decisions where to take sample, what is the most important samples. And sometimes you've been traveling for 24 hours to get in there. So it's a tough call. And then it's good to have some leverhead at home base, you know, that can sit there and see the big picture and help you out.
Yeah. Thank you. Bridget.
Yeah, I would just like to echo the support for improvisation. The University of Hawaii does not actively have a group that processes INSAR on a daily basis. We have several geodesists that study GPS data, but when this event happened, we just kind of stumbled into this process of working on this 24 hours a day. It turned out to be a pretty nice thing though, because the scientists at the USGS, at the Hawaiian Volcano Observatory, that would normally be the ones actively looking at the geodetic data, they have a large, great group there, they were called out into the field. Dawn can correct me if I'm wrong, but they were on boots on the ground doing some of the actual data collection. And so that left sort of this gap to fill in terms of stepping up and trying to contribute something that we normally wouldn't be in the spotlight to do. HBO would usually lead that. And the USGS has done a great effort in assembling all this data, but I think the fact that we were sitting 250 miles away in Oahu while this eruption was taking place and it not directly impacting us allowed us the flexibility to be able to jump in and contribute remotely.
Thanks for that, Bridget. So we're coming up to maybe 7 or 8 minutes left in the session, and this hour has gone really fast. I've really enjoyed listening to all of your perspectives, but I want to end perhaps on thinking about what do we need to do better. So I just want to go around all of our 4 panelists and ask that question: what do we need to do better and why? So maybe I could start with you, Diego.
Sure. Many things. I think from the sort of earthquake and tsunami early warning perspective, the communication of what it is and what it does, and the interaction with society at large outside, you know, the hallowed halls of academia is something we do not do well. There are a few examples in the earthquake community of agencies that do this well, and to me, there is one agency that does a stellar job at this, and that's GNS in New Zealand. The rest of us could learn a lot from them. So that's one thing I think we could do much, much better. The other thing I think in the US in particular we could do a lot better is how it comes to this issue of whether hazards in science motivate research. Is it top down or bottom up? I think in the US until fairly recently, the bottom up approach, the basic science driving everything else, is so entrenched in the funding culture of science. It's really hard to write a proposal for any meaningful amount of money that has hazards as the motivator. Just because there are some funding agencies that will let you do that, but most of the large funding agencies, they want to see the basic science question be the thing that drives everything. And you know, as we continue to overpopulate the planet, that seems to me an antiquated point of view. Of course, we should still have basic science, and that should still be really important. But I think hazards is undervalued as just the motivation of things. They want to see it in your broader impact statement that one day this will benefit society somehow. But you can't have that right now be the driver. And I think we should probably change that view.
Yeah, that's a very good point. Bridget?
I can't really add more to what Diego said. I completely agree. It's also sort of the aspect of, at least if you're an academic scientist, the rigor of everything else involved. But if you can contribute part of this aspect of hazard education into your teaching, we all try to do that, but it's really about getting through the basics and the textbook parts of all this. But those are the future taxpayers that you're actually educating in your classroom. And if you're teaching a large, broad audience course at the introductory level, you can always sneak in something about how you can pay more attention to your fellow seismologists or whatever that may be. Yeah, I find the same restriction though when I'm looking for funding. It's about the science and the understanding of the theory and how to process the data better rather than what to build in order to educate people better. It's important, and the program managers and panels want to see that in your broader impact statement, but it's usually not heavily integrated into the science proposal, and I'd like to see that change as well.
Great, thank you, Bridget. All good points. Siggy?
Yeah, I'm kind of one thing is monitoring. I spent a lot of my time as an early scientist trying to start some geochemical monitoring of volcanoes, and it nearly killed my career. It's really hard to raise money for it, and it soaks up your time and energy and effort. And I just have to, since we are all, well, this is geochemistry conference, I have to admit the geophysicists, they win when it comes to predicting, volcanic eruptions or these hazards. Usually they win. But our role in terms of thing is when it comes to cleaning up the mess after it happens. It's assessing the environmental impact and the cleanup. And I mean, in terms of very simple instrument, are these osmotic samplers that were developed within the oceanographic community at Southampton. Except you can just throw in your sample, just make sure it doesn't freeze. You can leave it in a river, and you can see a pulse coming in. And you don't need electricity; just put it deep down so the frost doesn't bite it. And that provides a very simple and cheap technique, similar to what you were discussing earlier, Diego. But I have to admit it, the geophysicists, they win.
I totally agree. And the last word goes to you, Don.
Okay, well, it's hard to think of anything different to say, but I would just say education, education, education is the way to ultimately prepare the public for the next big event, whatever it is, earthquake or tsunami or eruption. I worry about the Cascades in the US, for example. The eruption at Mount St. Helens in 1980, which I was there for that, took place 60 years after the previous eruption in the Cascades at Mount Lassen. And there were people adjacent to St. Helens who didn't know that it was a volcano. There was a generation or two that had forgotten what had happened in California. It's now been 40 years since the St. Helens eruption in 1980. That's a generation or two. The educational impact made by CVO has been tremendous, I think. But nonetheless, if there were to be an eruption, say at Mount Shasta, in the next decade or two or three, I'll bet there would be some people there that didn't think that Mount Shasta was a volcano either. So we just have to keep the pressure on. And luckily, both earthquakes, tsunamis, and eruptions are sexy enough topics so that if you can talk to the public frequently about it and keep them interested. Maybe not everybody is going to know, but at least through this enhanced education, I think we have a better chance of informing a broader range of people.
I think that's an extremely good point, and also a very good point at which to end the session after those wise words. And it remains for me to thank all of our presenters and attendees for a really great session, really thought-provoking, and I could have listened to you guys speak for hours. So thank you very much, and we'll be running this session again in 6 hours. Thank you and good night.
Thank you.